talking about is the fact that Monday is supposed to be a strike here, and I want to make sure the video camera will be at least manned. So I'm intending to give my lecture anyway, but you know, if you want to participate in the strike, since it's going to be recorded, any of you have the ability to watch it. So, you know, I'd like to see some of you here, but if I'm talking to an empty room with a camera, that's fine too. It's up to you. Okay, so where we were last time is basically having a differential equation, which I'm going to write in the form dl, say, at a position along a ray, and the ray is in direction omega. So this is the radiance at any position in any direction, and that's decreased by this extinction coefficient that could depend on position. And basically, I did it in terms of transparency last time, but if you think of this is the fraction which is removed per unit length. You know, it's removed from this radiance. So, you know, if the radiance is twice as much will be removed. This is the fraction. So this is, instead of just a change in transparency, the same reduction in radiance. And now we're going to add on the amount at that position radiated per unit volume in all directions divided by 4 pi. That's the emission added into the ray. And now we have to think about scattering. And so we're going to add on what the book calls LVI, the radiance scattered from the volume into the ray direction. And so I'm going to have to think about how we can compute that. First of all, it depends on the density of the particles, right? Because more is going to be scattered by the particles if they're denser. And it also depends on what fraction of the energy that hits a particle is actually scattered rather than absorbed. So maybe I'll put it up here. The albedo, I'm calling it alpha to be consistent with the book, because other people call it A, is the fraction of the extinction. Extinction is what's removed from the direct ray that is scattered rather than absorbed. So you can think of a sigma scattering is this fraction times this extinction coefficient. And that represents the fraction of the light that's actually removed from the ray that goes into scattering, and the rest of it, which is 1 minus alpha times sigma t, this is the absorbed. And this is the scattering fraction. Okay, but now most things like water droplets in the air scatter mostly forward. Whereas I think air molecules scatter both forward and backwards by Rayleigh scattering. Particles of colored confetti scatter mostly backward, right? Because they scatter in the side of that little bit of paper that's illuminated, which is sort of back toward the light source. So every kind of scatterer has its own phase function. So the phase function P, it could depend on position, it depends on incoming angle and scattering out angle. So here we have a ray coming in, flowing in direction omega I, and maybe scattering toward your eye in direction omega. Maybe I want to call this, like I said, I called that omega prime. And so if it's mostly forward scattering, that means the angle between these two directions, when its angle is small, they'll have bigger scattering. And if it's mostly back scattering, it'll be for angles where the angle is big between them. But in any case, this is the probability distribution function for scattering. And what that means is that the probability that light from direction omega prime scatters into some solid angle, say delta omega, is the integral over that solid angle delta omega of the phase function. I'll still put the position omega prime, omega, d omega, right? It's basically a distribution function, just like the scattering off of a surface. It's the analog of the BRDF of the surface. Okay, and what that means then is we can have the volume, what are they, the notion they, I'm not used to this, but it's the one in the book. L, the inscattering light, L volume inscattering at a position S, scattering into direction omega, is the integral over the sphere of possible incoming directions of the phase function from omega prime to omega times the radiance coming in to position S at direction omega prime. I guess in the book they would write it like that, and they would have an arrow here. In fact, I think they even have arrows this way too. D omega prime multiplied by sigma s, which is the albedo times the extinction coefficient sigma t. Right? Because this says how much light per unit length is actually scattered. And then this says where it's scattered. Okay, so if you put that integral over to here, you get a very complicated differential equation because the unknown L appears on the right as well as on the left, just like the Fredholm equations we had for scattering on surfaces. It turns out if I put this, well, shall I write, this is the full differential equation then. I'll leave off all the variables in parentheses. ds equals minus sigma t L plus the volume emission, which the book writes as E over 4 pi plus sigma s, the integral of the phase function omega prime, omega L s, omega prime, d omega prime. So that's the full equation. It turns out if you multiply this by an integrating factor, you can turn it into something that is a formula for L instead of its derivative. And basically that says that you're starting out at S equals 0 with your viewpoint, and you're going along this ray. And you're going to say that L at position S is basically L at position 0 times the opacity between 0 and S. That's the e to the minus the integral. I don't know, I write it. Oh, no, I'll keep it like this. I think they do in the book. So this is, let's see, how can we think of it? Maybe we'll start, since we're going in direction omega, let's start 0 at this end, and the light is actually flowing this way. And so we're up at some distance d to our eye, starting at distance 0 here. And so this is the light that came in at the far end, and it's the opacity along the whole ray, plus, now basically we're going to integrate this part. It's the integral from 0 to d of this E at position S. Now S is increasing that way over 4 pi, but it has to be each contribution of the volume emission, say in a little position here, ds, there's opacity in creating a transparency between this and the eye. So this is going to be multiplied by the opacity between position S and the eye at D. And this is ds. And now we're going to integrate this extinction together with the opacity that it got. So it's plus let's see, I guess it's sigma s times the integral from 0 to d of the phase function at that particular position, omega prime scattering into omega, times the radiance at that position coming in from that direction. And then we have to multiply it by the opacity, but also between S and D, from the scattering position up to our eye. And this integral was supposed to also be, maybe I should put the inner integral with respect to d omega. This is over the sphere. D omega, and you could think of this whole thing as being multiplied by the opacity between S and D, and then integrated over S, where we're looking at the inscattering position, inscattering at this position, say ds, and then modifying it by the opacity between here and the eye. So I'm not sure, I sort of wrote these integrals from my head. They may be integrated in the other direction in my notes, but it's basically similar to what's in the book. The way they do it in the book is they think of what would happen if you had all this light reflecting off a surface, right? So then they multiply this to find if there's a surface here instead of your eye, and this light is starting at another surface. So now that means this term is the radiance starting out at the surface here. I guess it's now 0, right? Because I'm measuring my light starting from here. That's the radiance leaving a surface. Then it has this volume emission and scattering effect added to it to create the radiance at this surface. Then if you multiply it by the BRDF and integrate over all angles omega, you can get the light reflected from this surface. And I believe that's the way it's presented in the book. So how are we going to actually do a calculation with photon mapping that's going to get this effect? Basically, we're going to think of modeling all the photons from the light sources. So either they're generated from discrete light sources from the sun, or they could be generated randomly in the volume if you actually have volume emission like a flame. Right? You have to have the photons starting per unit volume with a probability proportional to this volume emission term at that position, or starting at the light source with a probability proportional to the radiance at that position and direction on the light source. And those are going to be a source of photons. And then you just bounce them around. But you'll bounce them around not only on surfaces like we did before, where you save this incoming photon on a surface, but every time a photon actually has an extinction or scattering event, you'll store it at that position in the volume. So we were already storing the photons in this volume KD tree anyway, even when we were doing surfaces. So that part doesn't change. But what you have to do is, before we could track a photon from this bounce and assume it got all the way there with no problem, and then use the cosine or the BRDF or whichever way you could efficiently figure out how to scatter it. You know, if if a given factor in of the cosine and the BRDF isn't part of your probability distribution, then you have to, and it doesn't cancel with in the denominator with the part in the numerator, then you have to decrease the photon energy, say by the cosine if you scattered by the BRDF, or by the BRDF if you scattered by the photon. But sometimes, like for the Phong one I was showing, the scattering function itself is of a form where you can do it, including both. And instead, you have to scatter it on a volume. You have to track it through the volume till you see it should have an extinction event. And then you should either sample uniformly and multiply the photon power by the phase function and sigma s, or you could use sigma s as sort of your, how can I say it? Sigma s is A times sigma t. And your chance of scattering in a given position is already going to be proportional to sigma t. I'll tell you how to do that in a minute. So you've already got the sigma t factor from the fact that it actually stopped here and scattered. And then you can use alpha to be the Russian roulette. So you'll only consider it if this random number is less than the albedo, in which case you don't have to multiply by the albedo because you've already scattered it with that probability. I'm sorry, you don't have to. You divide the probability would be 1 over the albedo, but in the numerator of this formula, you're multiplying it by the albedo, so those would cancel, and you wouldn't have to worry about it, just like when you're scattering on surfaces. So then that means sampling according to this scattering function. And I think there's a formula in the book for the Hennier-Greenstein scattering function, which is something which has got an adjustable parameter that you can adjust for either completely forward scattering, mostly forward scattering, or uniform in all directions, or backward scattering. It's just a sort of a standard form to approximate scattering. And there's a formula that isn't in the book that's due to Schlick, which is just as even easier. And the advantage of those formulas is when you, first of all, it depends. If you have sort of randomly oriented particles or spherical particles, then if you talk about coming in this angle, omega prime, and scattering in an angle omega, then the probability of that scattering is only going to depend on the angle between these two vectors. Right? We have another angle, say if we make some plane perpendicular to this incoming ray, and we have a sphere whose north pole is along this ray, there's another angle, right, that's projected into this plane. This is this phi angle we've been talking about, azimuthal angle. It's going to be equal probability if these are spherical particles, or even if they're like snowflakes, if they're randomly oriented. Then on the average, the scattering angle is going to depend only on the angle between the incoming and outgoing directions. That's not always true. If your snowflakes are oriented so that they're hanging vertically, then maybe there is a dependence. In fact, I did a similar calculation for leaves in a tree, and I considered the case where the leaves in the tree are the scatters and they're randomly oriented, but they're all hanging vertically. In which case, it's not, you couldn't have this simple phase function that depended only on the angle of two vectors, but in most cases it does. So just like we found for like the Phong scattering, or even the cosine form, we just integrated it and found the cumulative distribution function, and then took its inverse to find out the direction theta, and then you choose phi randomly, and you organize a coordinate system so knowing theta and phi, you could compute this outscattering direction. So that's how you scatter. But how do you decide how far along this incoming ray you should actually stop for an extinction event? That's the tricky part. And the idea is, see, it's on one of these pages, probably earlier. Let's see. Okay. Let me start from the beginning, because it's related to what I did last time. Okay, here it is. The probability of not scattering up to distance s is the tau of s equals this integral x to minus the integral from 0 to s of sigma total scattering at position, I guess, u, say, du, right? This is the transparency we had before. And one thing I should have said last time is if sigma s, me getting a real eraser to do this, is constant, T of s is constant, this is just x of minus, this integral is going to be the integral of constant over an interval of length s, so it's just going to be s times sigma t. So the transparency varies exponentially, right? If you have like a thickness of smoke that removes, say, half the light, and then you have another thickness of smoke that removes half the light, what's left is a quarter of the light, and so forth. The amount of light is decreasing exponentially along the ray. So that means the probability of scattering up to distance, say before distance f, that's the opposite case. It's 1 minus this integral. Okay, so that's this thing is actually the cumulative distribution function up to s of the probability of scattering, right? Because it's all the probabilities of scattering up to s. And so you can make that be a random number xi, some random number between 0 and 1, and then solve for what this distance s is. So what is that going to say? That's if I say put the 1 minus xi here equals x of minus integral from 0 to s sigma t of u du, and then I take the log of both sides. You know, as usual, this could also be a uniformly distributed number between 0 and 1, too. We had a case before we had 1 minus one random number, and we just made it another random number. But in the book, they keep it 1 minus xi, so I'll call it that way. So we'll take log of 1 minus xi equals minus the integral from 0 to s of sigma t u du. And why don't I just move this minus to the other side? Right, so this is a positive number because this is a fraction less than 1, so its log is negative. And then I have a minus sign in front of it. So that means what we need to do is we need to step along the ray. First of all, we need to compute this random number and then compute this number, and then step along the ray incrementally computing that integral, say by Riemann sum, right, delta s times the extinction at that distance, until we exceed this number. You know, if you really want to be precise, you can take equal steps and then do some dissection or something to get exactly where it adds up, where it just hits, or sort of linear interpolation between the last two to estimate where it hits. It's particularly easy if this were constant. So that was S sigma t. So that means S is equal to just minus log 1 minus psi over sigma t for sigma t constant. So then you don't even have to step along the ray. You can just use this formula to figure out exactly where along the ray you're going to have that extinction event. And what that means is this extinction is proportional to the actual extinction coefficient. So you're generating these with the correct probability that way because you use that cumulative distribution function. So that's how you decide where to do these scattering events. And if this distance is longer than the distance to some surface that the ray hits, then you say, okay, the ray has gotten through the atmosphere, it hasn't scattered. Then you can instead scatter it off the surface and record the photon at the surface point instead of at this scattering point. So that means you have a volume density of scattered photons as well as a density on surfaces. So now, if you have an eye or a camera, you're going to do a gathering, right? If you trace this ray all the way to the surface, we talked about making a sphere on the surface, finding out how many photons are in there, say, make the sphere large enough to get 50 photons, and then divide by the area of the sphere, and I guess by 50 or something, however many photons you have. You get the average photon density, and you do a sum. I may not have the formula on these notes, but hopefully I do. What you have to do instead is if you want to look at the light absorbed and scattered into this ray, basically you're going to step along the ray, and at every step you're going to find a sphere. Say it's at this step. First of all, you're going to maintain a transparency, right? So you're going to, as you step along the ray, you're going to estimate this integral up to S by accumulating the transparency up to that point. And basically, if you multiply by the incremental transparency at each position, which is just minus sigma t dot du for each step du along the ray, and you keep multiplying them, you're basically accumulating the exponential. So if you've ever taken a course in volume rendering, say in scientific visualization, that's what you're doing when you're tracing a ray, and the volume emission is usually what you're doing in volume rendering. You're assuming you've got this colored emitting material that you're trying to render, and you incrementally step along the ray, accumulating this transparency at each point, and basically you're stepping along the ray doing this emission integral, if there's volume emission, and this scattering integral. And the emission integral, you know, I'm not going to talk about, usually you talk more about a smoke or fog-filled environment rather than a flame. But as you step along, you're accumulating the transmission so far by looking at, you know, for each little step, e to the minus some small x looks like 1 minus x, right? So you're taking 1 minus the local extinction coefficient, which you can think in volume rendering is called opacity, and then that's your local transparency, because this is the first order Taylor expansion. And so you're just multiplying a bunch of factors like that, building up this integral. So at each step along the ray, you're computing a new transparency by multiplying by one more factor of minus sigma t du, say if du is your step along the ray. And so your transparency star equals 1 minus sigma t du. And then you're adding on, or delta u, I guess it's a finite step. Then you're adding on the volume emission and the volume scattering. And the volume scattering, you're going to estimate by an integral similar to the one we had last time. You're going to grow the sphere in the volume until it includes your n particles. And then you're going to divide instead by pi r squared, you're going to divide by the formula for the volume of the cube. So basically an estimate of this term here L volume integral at some sphere center x going in direction omega is the sum I equals 1 to n, 1 over n, because it's an average of, okay, so we're going to have, we have to put the albedo in, because what we store is not the photon that was scattered out, but the photon that was coming in. So the chance of it scattering toward the eye has got an albedo factor times the phase function factor. That's probably in an integral that I write. Like the chance of scattering is always the sigma t. That's because the photon events are proportional to sigma t, because they were scattered according to this formula that makes their scattering probability proportional to the extinction coefficient. But you still have to multiply by the albedo because you save them in their direction on the way in, not what their power was scattering out. Because you want to be able to scatter them out into an arbitrary viewing direction after you've accumulated in the volume. In fact, you can move the camera and still use the accumulated photon density if you're not moving any lights and your camera isn't casting a shadow or anything. So we need the albedo, and I guess that albedo could be outside the sum. So you make the sphere big enough to have n photons, and then instead of the BRDF that we had the last time at x, we'll have a phase function. I wrote rho, but in the book it's p. P at x for scattering. Omega I is the direction of the stored photon into the viewing direction omega. And then if they don't have all equal fluxes, maybe you save the flux of that photon I. And then what you're going to divide by is 4 thirds pi r cubed. I should have asked any of you if you remembered this formula, but it's the formula of a sphere, volume of a sphere of radius r, where r is the sphere that's just big enough to contain these n photons. And so you're using the photon's direction because you're using this final gather is using the phase function toward your eye, just like the final gather last time used the BRDF toward your eye. And so as you build up this integral, you're building up accumulated transparency that you're multiplying by this estimate of the inscattering and the estimate of the volume emission. And finally, at the end of the ray, when you hit a surface, if there's significant transparency left, then you can start doing whatever kind of gathering you were doing of the photons on the surface to get the surface gathering part of that. Or, as I recommended last time, you can actually do an extra gathering by means an extra choice of directions around here if you think the surface photon map is bumpy. The bumpiness of the volume photon map isn't going to be as bad because you're sort of adding it up over this whole ray. So you're sort of doing an extra gather of a bunch of different things because you're gathering a bunch of different spheres along this ray. And it just occurred to me while I'm talking that you don't even have to make them equally spaced. As you get more and more extinction, you see less and less light. If it was really very dense smoke, you could afford to make them farther apart, I guess, so they overlapped less as you got farther away. In fact, this whole overlap is sort of waste, because a photon might count in this sphere and in this sphere. And you'd end up finding it and putting it twice in the sum. So another method called beam tracing is not to make a sphere, but to make a whole cylinder. Right? And then every time you have a photon that's in the cylinder, you have to figure out, what is the extinction from that photon back toward your eye at that distance along the cylinder, and add it only once. Another thing you can do is when you have your photon tracing, you're actually bouncing around inside this participating medium, but you're only saving the photons at these points. It could be that a track of one of those photons went through the cylinder, even though it started from a scattering point here and ended up at a scattering point there. So instead of saving just the scattering points, if you actually save this line segment, and then you have a sort of a beams coming through instead of discrete scattering events, and cylinders for the beam toward your eye instead of discrete spheres. And that would be a beam-to-beam estimate, in which case you would have to find, I'd have to think more about what sort of a volume data structure you would use to store these beams. You'd probably have to divide your volume up into a grid and have pointers to all the beams that intersect at each grid cell. So you could find the ones that intersect at the cylinder. And then, according to the extinction coefficient, if you do that, right, then things are no longer proportional to this extinction coefficient, right? Because they scattered at this position depending on the extinction coefficient here. So you'd have to, in your estimate, include this extinction coefficient as well, and then figure out, what's the length of the beam inside this cylinder and somehow add that contribution. And then you'd sort of have a beam-to-beam contribution. And the advantage of that is for the same number of photons, more of them intersect each cylinder, so your estimate will have less variance in it. Okay, so let me look through my notes and see what else I had to talk about here. Oh, bidirectional ray tracing can work for volumes too, right? You're starting rays from your eye. You're starting some rays from the light source, say from the sun, and they bounce around the volume in a certain directions and density of scattering depending on the phase function and the local extinction coefficient along the rays, because that's how we use this integral to find out, if this isn't constant, then we're stepping along the ray to find out where to scatter. And then we can start from our eye or our camera and take a bunch of rays and do Russian roulette to decide where to stop, and then we can join these points here. So when we do that, just like in the surface case, we've got the scattering probability and direction already accounting for the extinction, the albedo, and the phase function, but not at this point. And at this point, we have a separate phase function and a geometry factor. So the extra things we have to multiply by are the phase function of this dotted line for this direction to this direction, the phase function for the dotted line from this. I guess I'm going the other way, right? The light is coming, photons are going this way and scattering in that direction and coming in this direction and scattering toward our eye. This phase function, just like the BRDF has to satisfy reciprocity, the phase function has got to be the same going one way or the other by physics of conservation of energy. So it doesn't matter, actually, which way you're considering it. In fact, that's true if it only depends on the angle between two vectors, because the angle between two vectors doesn't depend on which you call the first vector and the second vector. So the fact that I drew the arrows wrong doesn't make much difference. So you have two phase functions, and then you have the extra geometry and visibility factor, right? Does this ray actually get through here without hitting an opaque surface, if you're doing the volume part of it? And if so, you have an extra geometry factor, which I believe is just 1 over, say this is x and that's y, 1 over rxy squared. There's no, that's the inverse square law factor, right? If things are farther apart, they're less likely that the thing would actually scatter in exactly that direction to that point. But it doesn't have this cosine factor that we needed for the extra geometry terms, because it's not a surface, it's a volume. And so you can do bidirectional path tracing also for volumes. So I've exhausted my notes of what I wanted to say today. I can write you the equations that are on the book for the surfaces, but since they're in the book, I don't think it's worth it. So I think I'll just stop early. But if you have any questions, I know one person wanted to discuss volume photon mapping with me in more detail because they were planning to do it for a project. That was you. Is there anybody else? Well, why don't I go to my office then and I can discuss it with Yukon there.